Welcome to Web Handling. My name is Dave Roysum. What better place to continue our Material Matters mini-series than with thickness? Thickness is one of the most common of the web quality tests. However, common does not mean commonly understood. There are many issues that arise with this simple measure, as you will see in the next few minutes. I know your time is precious, so let's get started. There are many reasons that you should be concerned with thickness. First, just as with basis weight, thickness is a most common quality attribute, machine setting, and test measurement. Second, just as with basis weight, thickness is related to economics. Perhaps half of the cost to produce webs is the raw materials, so losing tight control of thickness can mean losing control of profits. Finally, thickness is occasionally directly related to end-use performance, such as with absorbent capacity, box fill, as well as filter and gasket products, just to name a few. You might think that it is common to have a test relate directly to performance. Yet, in the majority of cases, tests are only indirectly correlated to performance, or, more likely, correlation has never been checked statistically and is merely judged to be important by someone in QA, often years ago. Yet, despite its popularity, thickness measurements are often ill-defined. There are dozens of standard methods for thickness measurements, and each will yield a slightly or largely different value. Thickness is especially ill-defined for materials that are soft or fuzzy, as we will explain in the next couple of slides. Materials where thickness measurements can be problematic include soft foams, nonwovens, textiles, tissue, and more. Let us begin by studying the most common measurement method for thickness. That is, to literally smash a web between a steel probe and a platen. As seen in the figure, the probe only touches the peaks of the tops and bottoms of the surface. As seen in the graph, the harder you smash the probe, the thinner the apparent thickness, which could be measured in any of several common distance units. In short, thickness depends on the measurement, which depends on the load duration, the probe size, and other factors that are hopefully codified by a test organization and controlled by QA. An alternative means of inferring thickness is far less direct, but is done by measuring the absorption of particles from nuclear decay. The fewer the particles passing through the material from the source to the detector, the greater the mass of the material in between. Of course, assumptions about the source strength, material density, the receiver sensitivity, and many other factors must be made in order to infer this thickness versus particle count relationship. Thus, the gold standard is to calibrate the scanner against the test lab thickness, not vice versa. Yet, measuring a single ply is not the only way to measure thickness. Stack thickness has many advantages over the more common single ply for certain applications. First, it has a better statistical resolution simply because of having a larger sample size. Second, it is a better predictor of box and wound roll behavior, where the product is actually a stack, not a single ply smashed between two smooth surfaces. Third, the thickness versus pressure, or more accurately, the stack modulus as a function of ZD pressure, is required by any and all winding models that have been used for the last half century. So, what is the relationship between stack and single ply measurements, holding everything else constant? For smooth materials, stack caliper is greater than single ply due to the entrainment of air between the layers, which could vary from less than 1% on a tightly wound roll of thick webs to more than 50% on a fluffy stack of thin webs. That is quite an uncertainty in thickness. For fuzzy materials, on the other hand, stack caliper tends to be less than single ply caliper due to the nesting and bending of the fibers on the rough surface. This relationship is also not small and has considerable material dependence. That can make predicting wound roll diameter and size problematic. Yet, the relationship in theory is an extremely simple equation. You could use it to predict wound roll diameter given length, or length given wound roll diameter, or thickness given length and diameter. However, in all cases, you will be needing and using thickness, as we just saw, and there are many different ways of measuring and defining thickness. The most popular of the 24 Abbott apps is the wound roll sizer. As shown in the screenshot below, you can predict length given diameter or diameter given length, as well as calculating roll weight, inertia, and other useful properties. It also converts US to metric units and vice versa in a single click. However, the big caveat is how to get and use and correct your raw thickness measurements. The online user's manual that I've written here gives tips on these and other plant floor application details with a single click at the lower right of the window. There is another complication brought upon us by the inviolate laws of physics. That is, with the inevitable thickness profile variation across any machine, you will quite possibly have unpleasant roll geometry issues to contend with. In the top figure, we have a web that has a variation of thickness profile coming from upstream that is high on the end and low in the middle. As seen in the second figure, if we wind these rolls on a common shaft or drum, which is most common, most of the thickness variation goes into tightness variation, while diameter variation is minimal. Our customer in the wound rolls themselves may not like that tightness variation across the width. There is another way to get near equal tightness across the width despite incoming web variations, but only if you have a special winder and can wind each roll individually. Duplex winders and salvage winders are examples. Here, the rolls are similar tight, but now we have diameter variations, and that could cause issues with our customer as well as with packaging and transportation. These physics are discussed in far more detail in my award-winning and trademark Web201 Advanced Winding class, so we will not need to do any more here. Here is a list of some of the more common thickness measurement standards taken from Appendix T of our must-have 750-page web handling handbook. Yet, this list is far from complete because entire industries as well as individual plants are free to invent their own thickness measurement methods. I once worked for a large company that had no less than a dozen different test measurements for thickness, and each gave different values. There are two starting points to learn more about material behavior and testing. The first is the 750-page must-have web handling handbook. We have an entire chapter on material properties and many pages of test standards in Appendix T that would be helpful for quality control, troubleshooting, and web handling work. The next is my award-winning and trademarked Web 101 class that has been taken by about 5,000 people just like you. Here you will learn which material properties are needed for web handling work and why they are predictive. Thank you so very much for joining me in this Material Matters series. Stay tuned for the next clip where we will talk about our most important property, thickness profile. If you have a topic you would like to hear about, let me know in the comment section below. If you found anything interesting or useful here, please like and share and subscribe. Also, please consider supporting the work of this channel using the Patreon link below. See you next time.